Today we are going to learn about implementing ensemble methods with Scikit-learn. This video will enhance your skills in building robust predictive models using ensemble techniques like bagging, boosting, and voting classifier. Welcome to our exploration of ensemble methods with Scikit-learn. Ensemble learning is an innovative approach in machine learning where multiple models, often called learners, are combined to improve the stability and accuracy of predictions. The primary advantage of ensemble methods is their ability to reduce variance, bias, or improve predictions, depending on the ensemble technique used. Today, we'll delve into three popular ensemble techniques: bagging, boosting, and the voting classifier. Scikit-learn, a robust library in Python, offers efficient and simple implementations of these methods, making it an ideal choice for both beginners and seasoned professionals. By the end of this video, you'll understand the strengths of ensemble methods and how to apply them to enhance your predictive models. Ensemble learning is a powerful machine learning paradigm where multiple models are strategically generated and combined to solve a particular computational intelligence problem. The core idea is that a group of weak learners can come together to form a strong learner. This approach is particularly effective in reducing overfitting, which is a common problem where a model performs well on training data but poorly on unseen data. By combining the predictions from multiple models, ensemble methods smooth out the irregularities of each individual model, leading to improved accuracy and robustness. There are three main types of ensemble methods: bagging, boosting, and voting. Bagging, or bootstrap aggregating, works by training multiple versions of a model on different subsets of the data, while boosting combines weak learners sequentially, correcting errors made by previous models. The voting classifier combines predictions from different types of models. The key to effective ensemble learning is diversity. Different models should complement each other's strengths and weaknesses. In practice, ensembles almost always outperform individual classifiers, especially on complex datasets. This is why they are a cornerstone technique for building robust predictive models.
Bagging, short for bootstrap aggregating, is an ensemble method designed to improve the accuracy and stability of machine learning algorithms by reducing variance. It works by training multiple instances of the same model on different random subsets of the training data. Each subset is created by random sampling with replacement, known as bootstrapping. The bagging classifier in Scikit-learn is a straightforward implementation of this technique. By averaging the predictions of each model, bagging reduces the error due to variance, making it particularly effective for models that tend to overfit, such as decision trees. This method increases model stability and accuracy, making it a popular choice for practitioners dealing with high-variance datasets. In Scikit-learn, implementing a bagging classifier is as simple as importing the class, choosing a base estimator, and fitting it to your data. By the end of this section, you'll know how to leverage bagging to enhance your predictive models.
Boosting is a sequential ensemble technique that builds models incrementally, with each new model attempting to correct errors made by previous models. Among the most well-known boosting algorithms is AdaBoost, short for adaptive boosting. The primary idea behind AdaBoost is to adaptively adjust the weights of the training data based on the errors of the previous models. Models that get the predictions wrong receive more weight, while those that get it right receive less. This way, subsequent models focus more on the hard-to-classify instances. In Scikit-learn, AdaBoost is implemented in the AdaBoost classifier. It begins with a weak model, often a decision tree, and iteratively adds models to form a strong learner. AdaBoost is particularly effective in improving the precision of models and is a go-to technique for many classification tasks. In this section, we'll explore how to implement AdaBoost using Scikit-learn and understand its impact on model performance.
Gradient boosting is another powerful boosting technique that builds models sequentially, much like AdaBoost, but with a key difference: it optimizes a loss function rather than correcting the previous model's errors. This makes gradient boosting not only more flexible but also more powerful. It works by constructing decision trees sequentially, with each tree being trained to predict the residuals or errors of the previous models. This approach allows the model to handle complex data patterns and interactions. In Scikit-learn, the gradient boosting classifier is used for classification tasks, while the gradient boosting regressor is used for regression. These classes offer a wide range of parameters for fine-tuning, allowing you to optimize the model for your specific dataset. Through this section, you'll learn how to implement gradient boosting in Scikit-learn and leverage its strength in capturing intricate patterns in data. Random Forest is a widely used ensemble method that's particularly effective for classification and regression tasks. It operates by constructing multiple decision trees during training and outputting the mode of the classes or mean of predictions of the individual trees. This helps in reducing overfitting and improving prediction accuracy. Random Forest is known for handling large datasets with high dimensionality, making it a favorite among data scientists dealing with complex datasets. In Scikit-learn, the Random Forest Classifier implements this algorithm with a variety of parameters to fine-tune the model. It is robust to outliers and can handle missing values, which adds to its versatility. In this block, we will dive into how to implement a Random Forest Classifier in Scikit-learn and explore its benefits and applications.
The voting classifier is a unique ensemble method that combines the predictions of multiple distinct models to make a final prediction. It can operate in two modes: hard voting, where the predicted class is the one with the majority of votes, and soft voting, where the predicted probabilities are averaged, and the class with the highest probability is chosen. This approach leverages the strengths of diverse models to enhance overall performance. Scikit-learn's Voting Classifier allows you to combine different model types, such as logistic regression, support vector machines, and decision trees, into a single ensemble model. By balancing the biases of individual models, the Voting Classifier can achieve higher accuracy than any single model alone. In this section, you'll learn how to implement the Voting Classifier in Scikit-learn and see its impact on model performance.
Parameter tuning is a critical step in building effective ensemble models. The performance of ensemble methods, like any machine learning models, depends heavily on the choice of parameters. In Scikit-learn, Grid Search is a popular tool for hyperparameter tuning that systematically builds and evaluates a model for each combination of algorithm parameters specified in a grid. This helps in finding the optimal parameters that balance bias and variance, thereby improving model performance. Whether you're using bagging, boosting, or voting classifiers, understanding and tuning the parameters is key to harnessing the full potential of ensemble methods. In this segment, we'll guide you through the process of parameter tuning using Scikit-learn and demonstrate how it can lead to more accurate and robust models.
One of the key questions in machine learning is whether to use ensemble methods or single classifiers. While single classifiers can be simpler and faster to train, ensemble methods often provide significantly better performance in terms of accuracy and robustness. Ensembles are particularly effective in handling noisy data and reducing overfitting, as they combine the strengths of multiple models. Through various case studies, it has been shown that ensemble methods consistently outperform single classifiers, especially in complex datasets with high dimensionality. By learning from these comparisons, you'll gain a deeper understanding of when and why to choose ensemble methods over single models. To solidify your understanding of ensemble methods, we'll apply the techniques we've discussed to a real-world dataset. This case study will demonstrate the practical implementation of bagging, boosting, and voting classifiers using Scikit-learn. We'll walk through the process of loading and exploring the dataset, applying each ensemble method, and then comparing their performances using key metrics like accuracy, precision, and recall. By the end of this section, you'll have a comprehensive view of how ensemble methods can be deployed to tackle real-world problems and gain insights into the strengths and weaknesses of each approach. As we wrap up our journey through ensemble methods using Scikit-learn, let's recap the critical insights we've gained. We've explored how ensemble methods like bagging, boosting, and voting classifiers can significantly enhance the accuracy and robustness of predictive models by combining the strengths of multiple models. The key to effective ensemble learning lies in model diversity, which allows the ensemble to generalize better to new data. Ensemble techniques offer substantial benefits over single classifiers and are an essential tool in the machine learning toolkit. We encourage you to experiment with these methods on your datasets and explore the vast resources available to deepen your understanding. Thank you for joining us, and we look forward to seeing how you apply these powerful techniques in your projects.